Hi everybody, this is my presentation for Lab 3 for Physics 2211. The purpose of this lab was to generate a unique star trajectory based on our email address and then analyze the star's motion to find the net force on the star for all points in the dataset. Then, using the results of the analysis, we had to estimate the mass of the black hole. The results of this lab found that the mass of the black hole was 1.764 times 10 to the 35th power. This was found by rearranging the universal law of gravitation to solve for the mass, which can be seen below. There were three major physics principles involved in this lab. The first was the momentum principle, which states that the rate of change in momentum is a result of the product of the net force and the change in time. When this is rearranged, the net force is equal to the rate of change in momentum over the change in time. The change in momentum is found by subtracting the initial momentum from the final momentum, and momentum itself is calculated by multiplying the mass times the velocity. The universal law of gravitation states that the force of gravity is a result of the universal gravitation constant, 6.07 times 10 to the negative 11th, times the mass of the first object times the mass of the second object over the magnitude of the distance squared. This equation was rearranged as seen below to calculate the unknown mass of the black hole. Here, the magnitude of the net force was just the gravitation force because it was the only force acting on the objects. Finally, parallel and perpendicular forces occur when an object is speeding up or slowing down and moving along a curving path. The parallel component of the net force is equivalent to the parallel component of the rate of change in momentum, which is equivalent to the change in the magnitude of the momentum over time times the direction. This force occurs when an object is speeding up or slowing down. The perpendicular component of the force is equal to the perpendicular component of the rate of change in momentum over time, which is equal to the change in the direction of the momentum over time, multiplied by the magnitude of the momentum. This force is present when an object is moving along a curved path. This slide demonstrates the Python code used to model the motion of the star. The star's mass was updated and the time was updated to reflect 1 day. The first while loop is responsible for computing the x and y components of the velocity by subtracting the indices. The second while loop iterates over the data values and calculates the initial and final velocities and the initial and final momentum, along with the change in velocity and the change in momentum. dp/dt was found by just using the definition of the rate of change of momentum, and Fnet was set equal to this based on the momentum principle. The next line was the calculation to find the unknown mass of the black hole. Finally, the parallel component of the change in momentum was found by multiplying the change in the magnitude of the momentum by the direction. The net parallel force was set equal to the parallel component of the momentum based on Newton's second law. The perpendicular component of the momentum was found by subtracting the parallel component from the total rate of change in momentum. The net perpendicular force was set equal to the perpendicular component of the change in momentum based on Newton's second law. Finally, the arrow scale was set to 1 times 10 to the negative 19th. Here's what the output looks like from the code. When the star gets close to the black hole, there are a few arrows that appear. The yellow arrow shows the direction of the net force. The black arrow represents the parallel component of the net force and points along the direction of the momentum. The red arrow represents the perpendicular component of the net force and points towards the center of the orbit at all times. The first question asks us to compare the parallel and perpendicular components of the net force to the parallel and perpendicular components of the rate of change of momentum. As we can see from the first equation, the rate of change of the magnitude of the momentum is equated to Fnet parallel based on the momentum principle. The magnitude can only be changed if there is a force component along the path the object travels. The second equation takes the rate of change of the direction of momentum and equates it to Fnet perpendicular, also based on the momentum principle. The direction of the object only changes if there is a force component that is perpendicular to the path that the object travels. The difference occurs conceptually. The parallel and perpendicular components of dp over dt are based on the results of the observational data, whereas the parallel and perpendicular components of the net force occur as an effect of the results. The second question asks us to imagine that the black hole whose mass we found earlier was replaced by a black hole with a different mass and to assume that the motion of the star remains the same. Could we determine the mass of the new black hole if the motion is only affected by the gravitational force of the black hole? To answer this question, no. It would not be possible to find a mass that is different from the original mass of the black hole. Since the position values are the same, the magnitude of the position vector is still the same, meaning that the velocity would still be the same, which would cause the momentum to be the same and the net force to be the same. So when we'd go to input the values in our rearranged universal law of gravitation equation, we would still get the same value for the mass of the black hole. Thank you for watching.